So thanks everyone for attending this talk. So the talk, as you can see, is running HPC and the AI workloads on the Grace Hopper superchip. My name is Rudy Shand, and I'm part of the Linaro Forge team at Linaro. And my role mainly is to help users debug and optimize their applications at large scale. So this is what the Grace Hopper chip looks like. It was released in May 2023, so it's coming up to 2 years since the initial press release. And I remember in the press release it was saying that by the end of the year they'll have a system based on the Grace Hopper. But it wasn't up until a year after the press release that the system started being developed. And that was because there was a supply issue, and it was very difficult to get the hands on the Grace Hopper because everyone wanted it, but there was only a limited amount of these hardware that was available. So what actually had to happen then, all this hardware needed to be funneled into specific systems so that they could actually build one of these HPC systems based on that. And they needed to get some of the HPC performance measurements out for the top 500. So they're really focused on trying to get one working. So they're looking back to where we are now. So there's a range of other systems that are now based on the Grace Hopper. So we have ALPS, which is the CSCS system that's based in Lugano, Switzerland. And this is a 2,688 node system. It's based on 4 Grace Hopper nodes, or Grace Hopper sockets per node. And it's quite a powerful machine as well. Then we have Helios as well from CipherNet. So this is the system that's hosted in Poland, in Krakow. And then the CEA as well, who has quite a big Grace Hopper system, and that's based in France. So apart from that, we have the Jülich system in Germany, which again is quite a big system. And there's also some smaller ones as well. So there's Isambard AI in Bristol, there's Romeo in France, and there's also Jedi in Germany. So all of these systems, they run a range of different applications. So they might run simulations for weather, they might run AI models, or also some national defense type applications, as well as for scientific research as well. Yeah, this one. So we look at the actual Grace Hopper architecture. So it's the first CPU superchip, and it was designed really to address the AI and HPC challenges for running these types of workloads. The chip has a Grace CPU, so this is 72 core ARM v9 Neoverse architecture, as well as the Hopper H100 Tensor Core GPU. And the actual main innovation of this is this NVLink, which is a chip-to-chip communication, which provides high bandwidth and low latency data transfers. And so what happened traditionally is you'll have your CPUs, and then you'll have your GPUs, which is a separate memory system. And what you'll have to do is go through the PCI Express, and you have to copy data from the CPU to the GPU. The GPU does all the calculations, and then that data has to be transferred back up to the CPU. But what the Grace Hopper chip does is it removes the PCI Express. So what you can do is the data is on the same memory, and you can just do your calculations between CPU and GPU. And this has completely removed the bottleneck that was initially posed by the PCI Express. So this NVLink chip-to-chip communication is 900 gigabytes per second of bandwidth, and if you read the white papers, it says that this is 7 times more efficient than the PCI Express. So it effectively removes that bottleneck. And this is the first technology that's been used for data centers, and one of the aims is to reduce some of the power usage, so to make it more energy efficient than some of the other CPU and GPU type architectures. The nice thing about this chip as well is it's very flexible. So if you have one Grace Hopper chip, what you can do is you can add more of these and connect these together to form a bigger node. And also, there's also some other offerings where you have sort of Grace alternatives, or you can put your x86 with a specific hopper as well. But the Grace Hopper is the Grace CPU and the Hopper GPU together. Then if you look at some of the programming models, so you can program the Grace Hopper using CUDA. So CUDA gives you access to the lowest level of hardware features, and you get kind of the total control between the maximum performance as well as really utilizing some of the features to make more effective use of your hardware. So as I said previously, what happens is you have your traditional heterogeneous hardware, and this is connected using a PCI Express. So what you have to do is in your actual code, you have to copy this onto your GPU and then do the calculation copy back, and that adds extra lines of codes. But with the Grace Hopper, it removes some of those codes, and this really does compact your codes. Yeah, so the threads, so on the NVLink C2C, the CPU and the GPU threads, they can concurrently and transparently access both the CPU and the GPU resident memory, and this allows the developers to focus on algorithms instead of the memory management. Yeah, so with Nvidia as well, you don't have to program just in CUDA, because if you program CUDA, you get that additional performance improvements. But what you might want to do is focus on portability. And the portability might be you've developed code on x86, and this might be using an AMD GPU. But what you don't want to do is just rewrite all your code. So you could use these OpenNP directives or OpenACC as well. And that kind of puts a high level of abstraction of your code. And when you transfer this onto the Grace Hopper, it's literally a transfer of the code, and the compilers for Nvidia will compile that for the Grace Hopper system. But there is a balance here between optimization and performance. So performance optimization and portability, because the more portable your code is, you're not necessarily making use of all the hardware features. Whereas if you're using CUDA, that's only specific to Nvidia and ARM, but you don't get the portability, which means you can only kind of port onto Nvidia architectures. So you have to have this balance between making the code portable and getting the most performance out of the actual hardware. So then the Nvidia SDK also provides a toolbox to access compilers in Fortran, C, C++, as well as core libraries, as well as math libraries for communication libraries as well. And these are optimized for the CPU and GPU, specifically for the Grace Hopper superchip. So if you're doing things like linear algebra or matrix multiplication, the toolkit will specifically compile that and make it optimal for the actual underlying hardware that sits underneath for the Grace Hopper. And there's a range of different libraries that is provided. So if you're doing things like maths libraries, you can use CUDA Blast, or if you're doing some ML workloads, then all of those are optimized for the hardware itself. And also with the NVLink chip-to-chip communication, the ecosystem really optimizes it for that as well. So you can make the most use between transferring data between, or doing your calculations between the CPU and the GPU. So this is actually one of the main points of what application developers want to do. They want to accelerate time to science. What this kind of means is they don't want to be held up by, you're running applications, you're going to put up with some software things, you're going to have to write software for your application, or you have system issues. And so they really want to focus on the application, focusing on the research papers, and having all the software side of it kind of managed elsewhere. So one way that HPC sites are making use of this is through SPAC. So SPAC, and what SPAC is, it's a package management tool, and it supports the software on a variety of hardware systems, or even heterogeneous systems as well. So the open source community, what they do is they have packages specifically for the Grace Hopper, and they'll develop that and build it, compile it, and make everything work really well for that. And then they will put this up to registry where other HPC sites can make use of it as well. So usually if one site is ahead and they've built all of these software packages, then another site can come along and they can just reuse that and be able to run the applications. So the example of this is a lot of applications were being developed for x86, and specifically scientific applications, and when they ported this onto ARM, there might not be specific wheel packages available, but by building this into SPAC and uploading it, it makes it available for everybody as well. And some sites have done some really nice things with this as well, where they have UN environments or put it into modules where you can just module load or load your UN. So kind of, if you're an application developer, what you can do is you can do UN image find to find your image, then UN image pool. So if you want to run your GROMACS, which is a molecular dynamics application, you can just pull that, you can start GROMACS, and then you can just run it and do your scientific application. So as an end user, it's very simple, but from a system admin, they do all of the work. And if you want to run a GROMACS on Alps, this is a job script, so it's using Slurm. And if you're familiar with Slurm, what it does is it takes care of the application distribution across the CPUs and the GPUs. So each one of these Grace CPUs is 72 cores, but a small number of them typically are used for the underlying processes, so things like running the runtime daemons. So all 72 cores aren't necessarily available. And this means that you need to change some of your programming styles. So on Alps specifically, what is recommended is if you have 72 cores, you want to kind of be safe and not exceed more than 64 OpenMP threads on a single CPU. So even if those threads are idling. And on the Alps system, it has 4 Grace CPUs and 4 Hopper GPUs, and this means that there are two threads per CPU, and you don't really want to ask for more than 32 OpenMP threads per rank to make efficient use of the hardware on the specific system. Okay, and also the way that system is set up, so if you have one Grace Hopper node, and the system actually has 4 sockets, and sometimes it is more efficient to just run on one node because of the NV link, and because it's so fast. But when you scale this up into multiple Grace Hopper systems, then the communication between those could be slower, which means that sometimes if you want specific applications with the overhead of running across multiple GPUs, it's better just to run it on one of those nodes. So they're looking at AI workloads, and what I found is that what developers typically do is they'll run their AI application on CPUs, and then get all of the environment set up for their AI workloads, and making sure that they have the right packages, the right tools, and that's working. And then they'll move that onto one GPU and get some more scalability and performance out of it to take their specific workloads and throw the ones that are more heavily compute onto the GPUs. And then after that, what they do is they'll scale this up to multiple GPUs. So actually the Grace Hopper superchip is really good for that, because you can start on the ARM CPUs, and then as you get more confident with your application, you can push that onto the Hopper GPUs on one, and then scale it up even further. So it really does reinforce that workflow that AI developers like to use. And also the AI community, they really do embrace containers. The problem is there's a whole range of different containers out there. You have Singularity, you have Aptainer, Shifter, Podman, and there's a whole range of different containers. And most containers are OCI compliant. So this is the Open Container Initiative, which means if you have a Docker file and you populate the Docker file, this should work across a range of different containers. And some specifically are developed for HPC. So there's in NERSC they use Podman, but then they've developed Podman HPC, which takes Podman but makes it more performant on the HPC systems, and helps with the usability as well, so people can use these containers more effectively on HPC systems. And the main reason why developers use containers is because it helps with reproducibility. With AI systems, there's a lot of tweaking going on. So you have your data, and your data has to be just right. And then you also have your model, and your model parameters need to be very specific. If you change one of those, then it could change the learning algorithm of your application. So what you really want to do is to kind of isolate the exact environment that you want using containers, and then you can just pull these up. And a typical workflow is you have a registry, you can upload all of your models and containers, so all of your models and all of your data, and then you can query that registry with the exact model that you want. And then you can develop that locally, and if you change some of your model parameters, you can upload that back to the registry as well as to make good use of it. So looking at nanotron training, what you see is it's quite complicated, and there's a lot of messing around with these containers. So one of the first things you do is you build or import your container, so using the Podman build, and then you can import the nanotron parameters that you need. You also set up an EDF file, which is your environment definition file. So this could be anything that describes the creation of the computing environment. And then you prepare your job, and this could be things like your YAML configuration, and this is setting up the actual model. So you see there's a lot of tweaking going on. If you want to use nickel, you need to set up for specific parameters for that. If you want to change a model, then you need to change this file, and also do the installation on top of your container as well. But containers are very nice for separating out the data and from the actual training of the systems. You might have some training data, you'll have your model, but then the system configuration might be completely different. So you can pull only the information that you want to train the model. Again, if you're familiar with Slow, what you do is you have your job script, and you'll have these specific environment variables to initialize the model. And then with PyTorch, you'll run that with the configuration file that you've pulled from the registry, and that will help you to run the actual model. But to parallelize your model across all the HPC systems, what you need to do is configure the actual PyTorch. So you might want to split by data, or you might want to split by the actual model itself. And if you split by the data, then you run this across one model, or you can split the model, but then have one data go through a whole range of different models. Okay, so finally, what we're touching on is debugging and profiling. So Robin's already given some information on that. But what you really need for a new hardware platform like the Grace Hopper is a really good tool ecosystem around it. For example, if your application developers are running at very high scales and then they run into a segfault, then it's very difficult to actually pinpoint that. And as we said, what we want to do is accelerate time to science. We don't want them to be they can't do the research papers, or they can't run some of the applications because of issues with the actual code. As I said, there's debugging, so this is DDT, and what DDT allows you to do is debugging at scale, so you can inspect all the environment variables and you can make sure that the calculations are correct. Specifically, if you're running some very big scientific compute, and you have to make sure that the calculations or the physics behind that is working as you expect, especially when you start scaling things up. So the way that this works is when you start up DDT, you can look at all the threads, and all these threads in the warp, they will execute in locksteps, which is typically 32 threads on Nvidia. You can play, you can pause all of your threads to kind of evaluate all of the environment variables. So some of the key features as well as this kernel progress view, where you can look at which threads have been scheduled or which has not been run yet, and you can kind of see if there's any stale data in your GPU. So, but this is really good in general for debugging the Grace Hopper. But if you want to get some of enough debug information out to be able to debug it, you need to run it with, you need to compile it with -g or lowercase g, and then minus uppercase g. So the lowercase g helps you to get the debug information on the CPU, and the uppercase g allows you to get the debug information on the GPU. And finally, there's Linaro map. This allows you to profile across all of the nodes, and you get this nice visualization across all of them. And you can see CPU time waiting from the kernels, which is this purple. And you can also look at some of the kernel activity graphs. You can also look at the time spent in each one of these kernels. So when you look at the main thread activity, the x-axis is time and the y-axis is how much time is being spent doing a specific activity. And if you want to compile the application, you typically want to do this with -3 so you don't have any of the debug information available. Then on the GPU side, you can look at the GPU utilization, so how well the GPU is being utilized, as well as GPU memory usage. I think my final slide is on. So my final slide is on the roadmap. So where we are now is in the Hopper. So I think the Blackwell has been there's been a press release on there, but that's not going to be available for another while. We still need to build systems based on that. So that will be the Grace CPU using the Blackwell GPU, and then later on there will be the Rubin GPU as well as the Vera CPU. So instead of it being Grace Blackwell, it will be Vera Rubin, but that's much later. So it will take a bit of a lead time as well for new HPC systems to be based on those. But the nice thing with using SPAC and using containers and getting the whole community together is that once the system has been built, and the community comes together and builds its packages for that and so it makes it a lot easier for anybody else adopting this technology to get a good start. And I think all of this really does further the acceleration for time to science. Great, that's everything from me. Is there any questions?